Oh yeah, that's fine. Yeah, sure. Yep. Totally, yeah. Okay, team, let's, what am I gonna, I'm gonna talk about things. Okay, so, is that okay? Yeah, all right, good. So, let's see, so I have a few fun things to show you. Just random things. I wanna show you more random things. I was gonna put, maybe I did put this up. I was gonna put, Zipf's law, right? We've talked a lot about scaling. I'm gonna show you it appears in even more strange places. So this is the popularity of chess openings. So, of course, someone analyzes this and we get a nice little power law, and so here are all these things, right? So games and sports are full of data and interesting statistics, right, to examine. So this pops up. This is Physical Review Letters, 2009. I mean, it's a strange world we live in now. Okay, so there's that one. That's about, this one is an interesting piece that's popped up again the other day. So this is looking at Twitter users, right, and showing that there are different scaling behaviors in the way they behave. I think it's to do with, if you compare things that are actually people, corporate, and then, oh, no Oxford comma, very disappointing. And then, I'm not sure if I can read this paper. Okay, so, sorry. It's just two parts of the world right there. Tells me something. Anyway, yeah, PLOS one makes a total mess of their figures and stuff. Oh, God. They publish about, well, a couple of years ago, it was 70 papers a day. This is a big open source journal now, right? I mean, one of the biggest, presumably. So it must be 100 a day, costs about $1,300 to publish, right? So you get that funding, and then it's there forever until the internet goes down and we all move to Siberia. Okay, actually Canada's much more accessible, tundra. Kidding. Okay, so no shutdown, it's all good. So this one will be about, so I mean, there's just a ton of things to look at. This one is, where are the figures? Where are the scalings? Ooh, that's pretty messy. It's power spectral density, of the activity, right? So the activity is different, basically, and there's a signature. So you can distinguish, and I think they claim they get about 85% accuracy. Okay. So this is a, standard deviation versus the mean, and I think, so these are humans, these are managed ones, like, corporate ones, and then these are bots. They have a very different kind of pattern. Humans behave differently, thank God. Okay, so that is something we can possibly really, use, because it's a good thing to sort out. Klaus Ett, who's an old friend of ours, a friend of the team, who's at Boulder, does lots of interesting things. He's in computer science, but I don't know, he had a paper recently on how big whales could be, in theory, given the ocean, given that sort of stuff, and shows that the blue whale is kind of within ballpark of what evolution could produce. So this is scoring dynamics across, I think it's basketball, football, and professional hockey. I don't know why baseball's not in here, and I'm not sure why hockey is. But then sorry, I know it's one of the four. Probably some big hockey fans here. Okay, all right. Of course, the thing that's missing is cricket, but we can forgive them. Anyway, so this is this is a big kind of patterns that appear across all sorts of things. The data is there, you can get at it. We have computers, it's very exciting. This will be a fun thing. So it'll be a nice project to work on, right? Any of these. Okay, so I think they were three things. I was going to show you, lots more things. Oh, this is totally good. I'm just going to show you lots of stuff. So this is kind of random. I'm just throwing this is what it's connected to. Okay, so in fact, so a few of us kind of came across this.
It's like within an hour of each other.
Yeah, I mean, I'd been meaning to put this in, and I've actually got it in the lecture notes now. So this fellow, Brett Victor, has done some really nice things. And so actually he took, as an illustration of making, in a sense, putting papers on the web properly and not being stuck to having pages, and thinking about how would you lay it out, and thinking about comic books, how the power of those things. So comic books, right, can really convey things that you can't do with writing or just with pictures. I mean, there's a really different kind of sense of information that comes through. So this is the Watt Strogatz paper. It's got things in here. The abstract's all there. It's just kind of nicely laid out, and then the algorithm is laid out, so you can play around with, right? So you can play around with some things like this. So this is P. Let me get it right. Yeah. So there you can see here's the random case. Here's the ordered one. So you can kind of check it out. Okay. So there it is. P equals 0. This is so some idea of what rewiring does, blah blah blah. And then I don't think this one is interactive, but yeah, I mean it's just a touch of what you could do, right? And so we talk about papers. I mean, I guess I do talk about papers should be apps now. I think it'd be kind of great if we could just produce papers that are apps, right? Instead of, maybe you have a PDF version that you could read a little bit of, but we're just not harnessing the power of what we could. And we don't have really good visualization things, right? We have lots of figure plotting things, MATLAB or whatever. We're fine with that, but it's much harder for us to produce really good interactive stuff. So we do for our papers now have what we hilariously call app indices, right? So online, so you have a paper and it points to an appendix, so you can go there and they're just simple things. So if you've got a ton of data and there are 10 million figures that get produced, you're not going to put them in your paper, but someone might want to go in and like click on, what if it's cities or it's counties or something, maybe you've got data like that, and you click on one of them and the information pops up, right? I mean, there's no other good way to display that. Tables that sort, I mean, very simple things that exist on the web. Anyway, so we're getting there. But this is a nice thing, if you want to go back and read this paper, this would be a nice little accompaniment. But it doesn't have, it's nicely, some extra notes here. It doesn't have the implications, or it's not the full paper. It's surprising that Nature hasn't tried to, get rid of him. Okay, so there are other efforts to put science into comic books so you can stay awake. This is actually a really potent one that came out of Japan, in fact, and so it's about Fourier. This is all about Fourier analysis. So there are a few others floating around. There's quantum mechanics. There's a whole series of manga comics, statistics, regression. There you go. Awesome. Not all of them are translated into English, but yeah, there you go. Manga guide to cryptology. It's just great. So great. Yay. Chibis. Yeah. That's what they should have, a chibi guide. Anyway. Manga guide to hydromechanics. It's just awesome. I mean, well done. Well done, Japan. There you go, DiffEQs. I mean, that would be a much better course, Put Easter eggs in everywhere. Somehow this front cover has something to do with semiconductors, complex numbers. Project management is hilarious and something that teenagers do. There's a magnet. Okay, there's a magnet. There's the Earth. Anyway, good fun. All right, so I think I have a few other things. Oh yeah, there's a cartoon guide to statistics. That's another one. That's a good one?
Yeah, it's a really good one.
Okay, yeah, that gets good reviews. Let's check out if Panda. I'm just give you a whole slew of madness right here. I don't think it is. I'm worried the Panda cam is not going.
Trying to get back to its trash.
What about the tiger cam?
It's being hammered.
So the tigers are never there for the tiger cam.
Oh, that's this one. Okay, I wanted to show you this as well. So this is, I'm just showing you, there's so much out there. It's just crazy. This is a kind of a speeded up version of the shipping from, actually it's the Royal Navy. So it's the Royal Navy where they went. Let me get it right. So this, you can see the date down the bottom. And I think it will start again. So it's kind of the First World War. They're kind of slowing down. What's going on? Come on, start again. There you go, pre-war, all right. I don't know, lots of good fun things, yeah. So there's some nice analyses of older shipping routes where you can see, oh, you can't, of course you can't see this properly. There are continents here. Where you can see when the captains of the Royal Navy or whatever it was did bad things. Their logs show there's some kind of gap, and they've gone off and done some trading on this is the 1700s and 1600s. I mean, there's all sorts of good fun things to dig out. So there's not just modern data, there's people putting together fun data sets from a long time ago. Okay, so that piece is embedded in your in the notes again. I better turn that off because I'm not sure how to turn this off. That should be able to. What do you think? What is this? What is this horrible thing? Kato DB. I don't think it's. All right. Okay. Nasty. Okay. Good. There's a smattering of things. Extra things. Good. Okay. Okay, so the projects, there are tons of things you can work on, right? There is the set of project slides. You can look through that again. Of course, anything to do, if you like coding, anything to do with Twitter, go for it, because we have 10% of all tweets, and we have them queued up in all sorts of interesting ways. Post-it notes, actually, yeah. So, nope, it's all on the VAC, so you can get in there and munch that stuff up. But we can talk some more about that, so please pitch an idea to me. One thing I will say is it can't contain anything that Malcolm Gladwell really said was okay. We've had some discussions about this, and since then, in the last week or two, there's been some good stuff about, he has this new book, and he's had to go on the defense because people have been accusing him of, just making a mess of all these interpretations, right, of science, because he goes and talks to scientists. So his defense is, in fact, he's a storyteller. He's not, in fact, giving real laws or anything, but his work is full of laws of human behavior, right? And it's very much how it's presented, to be construed as such. Anyway, so I just want to say that. A little bit of abuse. All right, good. So we're going to talk about small world networks. We've got most of the way through, and I was kind of speeding into this last part, which is a final kind of, let's see if that cam came up. That's very important. We may have to leave that in the background. Come on, PandaCam. It's just a disaster. Maybe PandaCam 2 is what we want. Start it. Why do you torture us, Panda?
They really don't do much.
No, I know. Should be easy to track them. You want to put one of those little things on. Not very exciting. Okay, so after, there's more to this. I mean, people keep doing work on small world networks, trying to explain things about the properties of them and the search algorithm, which I've laid out. But this is the last one I wanted to tell you about. So I'm going to zip through this. The idea was, right, so we have these bare networks, impossible to search, right? I mean, how do you do this? You basically it's just going to be a random process. That's the best you can do, particularly if your friends don't have millions of friends or huge capacities. So the idea is, well, people, you know who your friends are, right? You know something about their identity. So how do we capture that in a simple model? And we talked about these guys. So there's a huge amount of work that is available here about bipartite affiliation graphs. We touch on this a little bit. So we have individuals. They have some identities, and here it's occupation, for example. And so you can start to talk about distances between these attributes of them, right? So geography is an obvious one. I mean, you have to live near each other, perhaps, to get to. That's a very helpful way of getting to know someone else. It's not necessary, but it's always, even though we move around all the time now, and there's all this stuff on the web, it still remains a driving piece. So just to say again, this is the conceptualization of identity space. So people form groups. Right, so these are the people who, like Doctor Who, these are whatever it is. So in this little example, there are 6, and they have a distance of 1 between them, and then there's a distance 2. If you go up 1 hop to get to someone, there's a distance 3. There's some branching ratio for this tree that's, you could, in practice possibly construct these taxonomies, which are going to be ragged and complicated. We're going to stick to hierarchies generally because we like those. The idea was then, so you construct this hierarchy and then connect people with a probability that decays as a function of the distance up the tree between them. Xij, right, decays exponentially. We have some guy we can tune, this little alpha. So if we have alpha equals 0, we have random connections. Alpha is large, then this decays very rapidly, so it's the local nodes that are being connected to each other, right? So when alpha is getting towards infinity, it's just you just have separate little groups. Right, the little groups will always be connected. That was, part of the structure. There's actually, a little, generally a group of whatever it is, 6 to 10 to, we'll have higher ones, 100, I guess, as an example. But there's always a good chance that you connect to people in groups. Fine. Lots of sociological theory is sitting behind all of this. This is just to show that you would generalize it. Into other kinds of spaces, right, in which these identities exist. But then we have this, somehow we have them overlaying each other, right? So geography is a big deal, occupation's a big deal, age is a big deal. There'll be all these other pieces. They're not weighted as if this is the most important necessarily, right? We don't have that. There's a sort of a decay on top of that. So here's the idea now. So we had this example before with just one hierarchy. So imagine we have 3 elements to everyone's identity now, right? So this is hierarchy 1, 2, and 3. And so there's a node I and J, or individuals I and J, and we can write down their little identity vectors, if you like, right? So that's their position in this matrix, in this hierarchy. So we'll just label these groups as 1 through 8. So 5 through 8 are on this side, 1 through 4 on this side. And so you could give it a binary thing or something, but this is pretty simple. So in this first, so I has identity 1, 1, and 1. Okay, very simple thing. J has an identity 8, and over here it has 4, and here it's 1. So we can just write these out as 1, 1, 1, 8, 4, 1. And the distance between them, so I and J are far apart in this hierarchy. This is not something they match on, right? Whatever it is. Religion, I don't know, whatever you want. They don't match here. They're closer over here, and then they're very close in this regard, right? I mean, this might be sports teams they follow or something. I mean, people talk to each other, right? So that's a very great thing about it. Social, and the Google Circles point example captures this quite nicely. So the distance would be 4, 3, and 1, right? Because there's always a distance of 1 if you're in the same group. So there's a distance of 1, 2, 3 between I and J here, and then 4 for this one. And then just as so these distances of 1, right? I mean, you could imagine there's some, this is just completely artificial, but you could imagine maybe there's some weights in how you go up in this. Fair enough. We're just going to take it as these sort of unit steps. And then as an overall measure of social distance, we're just going to say it's the smallest of all of those distances. It's the minimum over those. So I and J are, and by this measure, quite close, right? Right? Because they match up in one of them. You could start to say things like, well, maybe people need 2 things. Some people sort of say this is sort of a bit of a folklore kind of thing, right? That it's good if you have a couple of reasons for matching up. It helps build a friendship, right? Because there's some reason they come together. That's sort of one of the dimensions. Then they find out they have another thing. You hate the New York Yankees equally. Whatever it is, you get to talk about that, right? Bit wheezy, people. Sorry. So you get to talk about that, and that creates a thing, and then maybe it builds from there. All right. Okay. So one thing, it's a funny measure. So one aspect that it picks up nicely, something that sociologists have talked about as being a feature of whatever social distance you could manufacture or come up with, is that triangle inequality doesn't hold for this measure, right? So I, J, and K have 2 parts of their identity, and in this aspect, J and K are very similar, but I is quite different. So maybe this is occupation, right? So this is these guys are lawyers, and this person's a high school teacher. So in some sense they're further apart. And then maybe we have geography. So these people live in the same suburb, and this one lives further away. Maybe they see each other through various local reasons because of the proximity. So the distance between I and J and K here is large. So let's see. So we have, this is the overall social distance. The distance between I and K, I should say, in overall, so there's a distance of 4 here and a distance of 4 here. So their social distance, the minimum of that is still 4. Right? So I is a high school teacher and lives in some place very different from K. And they just don't match up. They don't match up at all.
I'm sorry, why isn't it 8?
Why isn't it 8? Okay. So the distance between these guys is 4, I and K. And the distance between this measure of social distance, which is a minimum of all the individual ones. So the minimum, so the distance between I and J in this one is 4, and then I and J here is 1.
How are you counting 4 and 1 though? So I count up and then I count back down. That's
Oh no, so it's the height of the lowest common ancestor. Yeah, right? So there's taxonomy, and you go up the tree, and at this point they're similar. But you get a, what's that?
Wouldn't that be 3?
Okay, so this extra piece was that, where did I say this? You get a 1 for being in the same group.
Gotcha.
So your distance isn't 0. It's like Addish or whatever, right? You're 0 to yourself, depending on your personality. But this is, you could probably, okay. But it's 1 is the idea.
Okay.
Discrete human beings. You know, maybe that should be 7, I don't know, right? On some units, right? What we're trying to do is add identity in some way. Okay, let's see. So we're doing all right? Sort of? We're trying to understand this one? Okay, so distance between I and j, again. So you get a 1, 2, 3, 4, and that's the height of the... So you can imagine all of these are hanging off here. There's another level to the hierarchy. Okay, just for simple, yep. Like there's a little... That's probably the way to think of it. So the branching ratio of 2 and then a branching ratio of 6 at the end. Think of it like that. Okay. All right, so the distance between I and j over here is 4 and I and j is 1 here. Okay? So then their social distance is going to be 1. It's the minimum of those two. Right, they live next to each other. J and K, they have the same job. They work at the same place. So they have a distance of 1 here, but it's far apart here. So that's not bringing them together. But this does, and so their social distance is also 1. So we get 1 plus 1 is 2. So triangle inequality. Right, normally we have this kind of, we'd like this sort of thing. This distance, right, ik should be smaller than the distance of ij. Right, so to travel from here to here, but you're going from a high school teacher who lives, you know, I want to say a silly place, but let's see, in Princeton, right? And this one also lives in Princeton. So we've got this high school teacher, lawyer who works in the city, right? So that's how these guys connect. And then, and this one lives in Princeton, so that's their connection. That's their connection. And this one lives in Poughkeepsie, because that's funny to say. Okay, how about that? Or Schenectady, somewhere like that. Okay, so these ones are they're very far apart in terms of this hierarchy. They're actually sort of as far apart as they can get. So, and that's pretty common. And so what it means, and you know this, right? So social networks are kind of strange, right? You have a friend and you start to see their friends in some way, or you hear about them. They can be really completely different to you. I mean, there's lots of reasons why they might have similar attributes to you, but you can, they tell you about your crazy friend who does these X, Y, and Z, and they're just very different. So it also means then it gives you a sense of, right, so you make this hop in a social network and then maybe a few more, you're very, very different people. I mean, not very far away, because you can basically kind of go around corners in weird ways.
How do they get if you try to do analysis on these things without the triangle inequality, I feel like you might end up in a bad place.
Yeah.
So how do they get around that?
Yeah, you're in trouble with the metric thing. Yeah, right. So you just feel a little sick about it, and you simulate things. Yeah. There's probably some good analytic stuff. So this is one of these kind of models that's in between something that's analytically tractable, and I mean, you can make some changes to it to make it solvable, and we did some things like that, but mostly we did simulations on top of it, because it's hopefully understandable, or it's not too many pieces, so you can kind of believe what comes out of it. I mean, yeah, it's got all sorts of problems and so on, but it's pretty simple. So is that okay? You can't bring all that good stuff with metric spaces. You can't. That's out. It is a kind of distance measure. Yeah. But it does have. This is a real feature of social networks, right? I mean, this is something that was expressed by people thinking about social networks, but not put into a sort of a hard measure in some sense. Not that this is exactly how it works, but this is at least a written down thing. a model, but it captures what's intuitively understood about social networks, right? That you go to a friend and then their friend, some of their friends are just a very long way away from you. Yeah, yeah. The space is kind of a weird space. Cool, yeah. Right, so, all right, so we've had this kind of stuff before, so this is based on Kleinberg's work. So how do we search, or how can we reasonably do these kind of distributed searches that are underlying these small world things? So you know your identity of your friends, and the target, that's the game, right? So you essentially in this model, you're given the vector of the target. And so now you have a situation where you can actually estimate the distance between your friends and the target. Right? But they have identity vectors, and you can just look at them and see which one matches up the most. Right? Who has the smallest social distance? And if you have them being equal, then you can do something random, randomly choose, or you could look at the one who matches up the most. I mean, if you have 6 identity attributes and you have a friend who matches up with 5 pieces, with the target, then you're going to send it to them, right? Okay. Yeah? You have a reason for sending things on, and it's just a very natural thing. I mean, it's what people do, right? If someone says you've got to get it to a lawyer in Boston, then you think about, you don't send it to your, parachute instructor in New Zealand, right? You don't do that. Yeah. So we're going to use a greedy algorithm as per Kleinberg, and we'll introduce this piece again that was really in the experiments and really in the natural situation that things are going to fail randomly. So we're going to have, this is the Q is going to be what we define. This is our success. This is the probability that we get all the way through. And so again, alpha is, so this is going to be 100,000 nodes, which is just, individuals, just as an example. This is an arbitrarily defined kind of success rate, 5%. And we have, what is the attrition rate in this one? We'll put in the attrition rate of that we had in the experiment, actually, sort of 0.37 was the success, 0.73 for the probability of failure. So we see a kind of a crossover here. So what happens is, blue here is the alpha equals 2 case, and alpha equals 0 is sorry, it's not the blue case, it's this curve here is alpha equals 0, this curve here is alpha equals 2. So so above this, we're going to say it's pretty searchable. 5% of these guys get through. So this is something that, it's not a p-value. It's just sort of not a bad success rate. It's not a disaster. And it is this kind of thing that fails, right? We have this kind of exponent. We have this problem of, the message has to keep going. They're all just single chains, so they're brittle in that sense. If you imagine if you just allow people to send 2 messages and branch like that, a little bit of spamming, which is a bit dangerous, then things would change a lot again. So what's happening? Across here is let me explain this properly. So across here is the number of hierarchies, so even out to 15 hierarchies, and I haven't given you all the details about those guys. So this is just one hierarchy out to 15. So this one hierarchy is an interesting case. So now you've just got individuals, and of course this is random. There's a random start person, a random target person, which generally means they're going to be a long way away from each other. So they start sending things up and down the hierarchy, essentially, is what they're going to be trying to do. And this will work. Having one hierarchy is good for the alpha equals 0 case when you have lots of long-range links, random links between nodes. That's somewhat searchable, right? There's only one hierarchy, and then you just randomly add links between people. So essentially, the hierarchy doesn't even really matter. You're just sort of randomly adding links. I mean, it does in this. Yep. You just randomly add links. People still know the identity vector. All right. So they can tell if the target person is 15, they know which of their friends might be closest to that in the nearest sort of division, if you like. So for one hierarchy, that case works well when you have random links. But as soon as you add more hierarchies, it becomes kind of not so good, right? You get this problem of overshooting and so on. For the alpha equals 2 cases, which is much more realistic, so now you're connecting to individuals, so this is alpha equals 0, alpha equals 2, you're connecting to nodes nearby, right, relatively, and maybe, you'll have a few longer links and so on, but it's more social. You're connecting to people who have a similar identity to you. So that's more social. This whole curve here applies to a very non-social kind of world. So you'll get nice clustering, all sorts of things. So this one here is non-social. So what happens is as soon as you add a second hierarchy, you start to have searchable networks. Eventually it decays, because eventually the problem is if you weight all attributes, if you have 100 attributes, then, and because of the construction of this, the target is going to match up with all of your friends on one of them somehow, randomly. So you don't know what to do anymore. And of course, it's not how these things really work, or how you would navigate properly. You would focus on, as we saw in the real experiments, geography and then work. There'd be, you would actually weight them in different ways.
So H is referring to the circle, the type of circle.
This H here, this is the number of hierarchies, right? So this is H equals 2.
Like different circles.
Yeah,
So like the
different kinds of circles, yeah.
the left one is
Work,
and the other one is where you live.
geography, yeah, right, exactly, right? So now in this case you have, there are 9 attributes of people. Work, geography, the sports, whatever it is, right? And you've given, this model, it's a model, it's obviously inherently wrong. You're weighting everything evenly as well. You're giving, is that, okay? So, another thing that's not being shown here is that, okay, so you make these weights in one hierarchy. So let's say we have a second hierarchy. So here are all the nodes. They're aligned like this across the n. The thing that we did, which is the simplest thing you could do, but of course you could improve upon it, is randomly shuffle everyone across hierarchies. So that gives us a bit of a gain, right? So if you so you take all of these individuals and then you put them in the second hierarchy, you randomly shuffle them, and then in this new one, of course, you reinforce the local connections again. So that does build in a kind of long distance aspect to it, because the people who you're locally friends with in this dimension are going to be scattered across here, and maybe you end up over here, so these people that you're friends with in this dimension are randomly scattered in this one as well. So it gives you a way of hopping between worlds, right? It gives you this you've got one attribute, there's a bunch of people around you, and some of them will be similar to you on other attributes, but in this model, as soon as you step over to this other attribute, everything's scrambled. A whole bunch of new people appear, right? So the people you play basketball with have nothing to do with the people that you live with, right? Or live near, okay? I mean, obviously, this is testable and so on. Okay, then we did a rather brave thing where we just for fun said, let's try some numbers that kind of look like Milgram's story. And so what we did, remember it actually started at 2, we took the successful chains for his experiment for the ones that went from Nebraska to Boston, because that was a bigger distance. So we took out the 100 or so, it's about 100 that came from Boston to Sharon, right? They were a bit too close, so we took them out. And so there's a couple of hundred here. And this is a fit from our model, which is kind of hilarious. I mean, obviously you could game this in various ways, but the point was we get basically that shape for a pretty wide range of parameters, which is what you might hope with a simple model. That there's a big sweet spot, right? It's not we've talked about this a little bit, it's not a sharp point where everything magically works. It's a pretty big spread. So we have a branching ratio of 10, right? So the hierarchy for each category is a branching ratio of 10. We just had 2 attributes, so that's a bit like geography and work, kind of they're the big main ones. We had alpha equals 1, which is the so it's decaying but not super fast, so it's a bit generous. These are informed by actual studies of people. 300 is a typical number of friends that people have, so we distributed 300 friends connections in each one, groups of a size 100. So this is Dunbar's number sort of thing, right? So there's some anthropology sticking in there. This is from work by sociologists. asking people how many friends they have and doing clever things to find out if that's reasonable. I think the number was actually 291, which is a little specific. But and 100 million was the population of the US in the late 60s. So I mean, we actually did kind of put in some, semi-realistic things. And so we get, this was the data, 6.5, and our model had 6.7. It seems highly cooked, but I mean, we didn't just pretend that there were less people or right. I mean, there were those sort of citable references. The ones that are completely, the ones that are much more made up are these ones. But we could show that this had a fair amount of flex in it, and these weren't too bad either. I think, if alpha gets to be too high, then it's a little too closed in, but not bad. So that, this was a paper in Science, and this was sort of one of the, maybe a clincher for that paper. Anyway, so some pseudo connection. So there's some, of course, work that's been done since then. Right, and exactly this paper was the one that inspired the Red Balloons work, right? The DARPA work, the DARPA Grand Challenge work. So Lada Adamic, I want to say Adamic, but I think it's Adamic, who's done all sorts of nice things. So they took this work and went and looked at a real thing, which is always very dangerous, brave. We didn't do that. So she was at HP Labs then, and they looked at how people are connected as a probability of a couple of things, right? So one was organizational distance. So they got out the organizational chart, very reasonable thing to do. And so they have an exponential distribution popping out for that. Right? I guess they must have asked, I can't remember, we could see I need the reference for that one. I think they might have looked at email connections and so on to see who really talks to whom. And then they found a different thing for distance. So they looked at where everyone sat actually physically in space. And that was more like a 1/r. So that's a different kind of, we just posited this exponential decay in the hierarchy. And then of course you have to talk about, so that's okay. That's okay. So it's a bit of a mixture. This is a bit Kleinbergian. This is a bit more like what we had. We talked about the DARPA thing. There are a bunch of other things that follow from this though, that are at least supported. Right, putting for information, moving away from people, but looking at informational objects. So having people put tags on them. Of course, the metadata of a lot of things is actually the document, But things like pictures and videos, people tagging them, give them real, very helpful little hooks. So then you can start to lay them out in some way. So they become things that you can navigate around. Website tagging goes through Bitly. Lots of other things. Flickr, of course. So this word isn't used so much, but this it's a collaborative thing that's happening. People are tagging, and ideally they do it without other people knowing. But usually you have completion things that kind of suggest how you should tag things. So there's a rich gets richer issue there, right? So whenever you see that, I mean we've seen this quite a bit. We'll see it again with small world networks, scale-free networks. That reinforcement mechanisms is that you just need to look at whatever situation you're in to see if people are acting independently. I mean, there are really simple things like voting, for example, right? So this is a kind of voting for a particular characterization of something. So if you get to look at a picture and then independently put in your tags, that's a good thing, right? You're independently acting, right? But if sometimes you see this in meetings, and you probably don't have to go to so many of these, but they're big meetings and people are discussing how they might do something, and they say, okay, let's put up all these possibilities, and you get this is people like this one. I'm sure McKinsey thought of this, but you get, or some other possibly lesser consulting group, you get maybe 10 little sticky tabs, right? And you're allowed to go and put them as votes. You put them all in one box if you want, right? So you get to distribute them. But of course it's sequential, so you get to see what everyone else has done. So the first people start to set things up. We'll come back to that later on as part of our study of success and so on. Anyway, this is just part of what comes out. Obviously, Amazon is a big story for search, navigation, search kind of thing. You can see how it's working. And then you have that battle between what does your average human know versus the experts. The hoi oligoi, I think it is. The few. Anyway, hoi polloi, it's good. All right, so nutshell. Straight up networks, without any structure on them, especially social ones, are pretty much unsearchable. You may have some hope if you've got some huge hubs in there, but then it's cheating almost, right? Yeah. I mean, if you the extreme is one big star, right? So it's just one node, and everyone's connected to it, and you just send it to the node who's like, push, But that's basically what it's doing. That's really what's going on. So, we've given an argument in form of a model. So there's a slightly more elevated form of presenting something than just talking about it. You can do these simulations again. So identity is this. So if the nodes themselves know about how their network is structured in some way, and of course for us it's identity. So this leads to, we're getting into the cusp of better social network models. We don't quite have, I still think we don't really have a good toy social network. We usually tend to usually what happens in big papers about networks now when you're trying to show something general is people just line up 50 networks, everything from yeast gene networks to organizations, board of directors to what else? Dolphin social networks, just anything they've found lying around, just do them all. Here's the internet. Whoop, we'll put that in. Here's the the neural network of a worm. Whoop, and just test everything on those and show maybe there's some that's one way to do it. But it does suggest we're a little bit unclear. All right, so these peer-to-peer network type things, it helps you, reinforces what people have probably naturally done, but it gives some support for how you might construct them, how to construct informational databases, and now, of course, how to mobilize people for your social cause, good or evil. All right. Incentivization, yeah. Okay, so we're going to move on to scale-free networks. So this is the second big piece of the sort of the initiation of this giant story on networks. Again, so this is 1999. Okay, yeah, and was very exciting because you can actually do some things. All right, so very simple thing: power law, degree distribution, right? Decaying degree distribution. As a power law, then we have this term scale-free networks. So it's absolutely specifically about the degrees. And I'll repeat a few things I've said before, but so what you're doing now is either you have a network and you take all the degrees, you count them up and create a big histogram essentially, look at how the tail behaves, or you have some simulated one and you're sampling from it and so on. So I've mentioned this one. It's more now, isn't it? I keep, yeah. So, right, emergence of scaling random networks. So, okay, so I've talked about this in more general terms, but yeah. Laszlo Barabasi, who's a very big character now in complex systems, he's at Northeastern, Rick Alberts at Penn State. Done a lot of very interesting, lots of all sorts of different things. I mean, Barabasi's got stuff on human behavior, like the letters sent by Einstein. I mean, these things are debated and discussed, and there's some typical kind of academic madness about it. But so it's Darwin and Einstein, the letters, their response times, what were they like? So again, you get heavy tail distributions and why that is. Tons of other things. I mean, just a sort of a huge litany of work. Lots of stuff now about citation structures. Like, can you predict whether a paper will be successful or not? What's its typical trajectory? Which is, great. It's a very interesting piece. All right. So they're not. This is just to say they're not fractals, right? This is not what these things are. We think of scale whenever we see scale-free. We get excited about fractals. Although I've loaded you up with power law size distributions, we'll get to scaling in general later on. So it's really usually about, so of course it's not the physical shape. There are some networks that kind of have that, and that's a different business. They're usually in some ways they have to be non-physical. They have to be kind of technologically There has to be a technological aspect to it, even, or pure informational, such as words connecting to each other, like pure ZIF distributions and so on. But things that not necessarily even technical. But okay, so that's kind of the structure underneath them. Google, for example, right? That website, huge, but it really then is a giant farm of things. Yeah.
In Meg's class, she said that there was a study in Scandinavian country about.
Yeah. So that one's not so good. Okay, so there's a.
That was pretty physical.
So it's the claim that there is a power law size distribution for sexual contacts, right? Okay, it's for Sweden, and we could dig it up. It's very few orders of magnitude. Got published in Nature, I think. So that I know two of the people who wrote a rebuttal to this saying that you just did not do this very well. And one of them, it's a very odd side note, used to live in the apartment below us. Jamie Jones, he's now at Stanford. And he was an evolutionary biologist who went off to Indonesia and took about 6 weeks to get into somewhere where he'd studied orangutans for a year, and that was the last time I saw him, and then he reinvented himself as a social scientist. So anyway, now he's at Stanford. But I could put you to some rebuttals of that. It's exciting for people to read that one, but it's not a lot of orders of magnitude, and I'm not sure about the reporting for that one. There's obviously potentially an aspect for, there's a professional aspect involved that may get the skew right out there. Anyway, all right. Okay. That's a physical one, yeah. But again, all right, okay, all right. I'm going to say it doesn't fit. Damn it. All right, so hyperlink, you're right, I mean, the web, right? The web is a great example. It's a little more complicated than just one of these scale-free things, but the in degrees and the out degrees are different. They have different distributions. Interesting things there. There's a ton of, as you've seen, right? These are controversial things. It's hard to measure. It's hard to measure power laws. Everyone also gets excited and thinks everything is a power law, for example. And so there's a lot of that. Anyway, so here's something from the original paper. This is the three pieces they highlight. What do we have? This is the first one's the actor one, right? Yeah, so this is the actor collaboration graph, which is, as we've that was in the Small World paper as well, but it's really crazy, right? So if you're in the same movie, then you're connected. What do we have? 1, 2, 3. So this is 3 orders of magnitude here. This is really 2, maybe kind of 1.5, where, right? This is pretty thin. This one is for Notre Dame, which is where Barabazi was at the time. Reiko Albert was a graduate student. Let's see, so that is, it doesn't say, but yeah, this is Notre Dame. So this is the number of links between web pages, I think. Typical kind of thing, right? There are 200,000 vertices. The average number of links is 28. It's not so many. That's for the actor. So that's the actor graph, which is a bit strange. So this is then the web, some piece, a very small piece of the web, 300,000 nodes, and then an average of 5. I can't remember what they did with links, because these are directed links. So they must have just said they go both ways. The model they have is for undirected links. And then the power grid. And, actually, all right, so they do report them very sneakily down here. So the power grid, so 2 of these things were in the Small World paper, right? This is the only piece that's different. So instead of C elegans, there's this. And this is 1 order of magnitude here. So it's a bit shaky because, I mean, that's, I don't know, maybe 1 order, barely an order of magnitude. And the exponent here, they have 4, 2.1, and 2.3. So these guys are, these ones are kind of in this interesting realm, right? They're actually getting right down to the very bad realm, where the average size of things is quite large, okay? Right, 2 is the cutoff. But 4 is very fishy, right? So 4 is, maybe this is something else altogether. So as soon as you go below over 3, you're like, well, I don't know about this. So I think this one turns out not to fit that. And this is, of course, a very physical network. It's really, so it's hard even to get out a map of the internet itself, the physical structure. That's something that people struggle to get out. Doyle, our fellow Doyle, who we talked about with the HOT model, the highly optimized tolerance, did a lot of work and argued with these guys a lot about the internet in particular. I remember seeing at Santa Fe, like him going out at them. Fun to watch. But, so I don't know about the web, maybe we've got there now, I don't know. There's a lot of, messiness in figuring out, are you talking about a router or some, what's a node in that thing? Okay. All right, so this is the original one. That's the inspiration. This is these exponents matter, 2.1, 2.3, and 4. Okay, all right. So here are a couple of artificial pieces of scale-free networks. This is something where gamma is 2.5, right? So you've just simulated at least a distribution like that, actually in this, right? 2.5 is the exponent. And this is then, so these are simulations. There are, not many nodes in these. I think maybe 1,000, something like that. And then we take the largest component, right? So there's going to be some tiny little bits hanging around. And then, so it's sampling from this distribution and then connecting them with that random rewiring thing. These aren't grown or anything. This is just a random rewiring thing. So you see the kinds of structures you get out. Some of them are very thin and tendrily. Didn't work out that well. Some have more of a, some have sort of a clear main hub. There are a couple of hubs in these ones, So this is the problem with sampling from these things. If we were doing pure random networks, they'd all be very similar. But these have some, accidents of probability, basically, right? So this one is a much bigger node than probably anything in here, right? Because this is a 100-year flood, the 1,000-year flood thing. You're sampling and sampling. And so these are a little hard to build because you do have hubs in them. But that's, scale-free networks, you can, I've talked about these horrible messes and how you shouldn't look at them. At least in some simple cases, you can you start to see that there's, but the best thing to do is get out the degree distribution. Just look at that, right? That's what you do. Okay. All right, so we're going to bring in a mechanism again, which we were so sort of fond of with Simon's model, highly optimized tolerance. They're real mechanism-based stories. Self-organized criticality was not. Small world networks were not. So we had these three examples in the original paper, and of course, since then, a bazillion networks have been analyzed. But 2.1, 2.3, and 4. So how are those exponents coming out? Is there some reason we're getting those exponents? Can we tie it to something about how the thing's being built? And we would have that, the active collaboration graph. You have a history. You could build its growth. You could reproduce its, ontogeny. You could do that for the web. It's a bit harder, but you could do it for the web. It's a bit harder. In principle, you could do it for something like the power grid. Neural networks, maybe you could kind of look at the older things. Of course, we saw that for the Linux kernel, which is a network story. Okay. So this is our universality problem. Like, do the details matter? All right. So, okay, good. I've alluded to this earlier on, of course, because we talked about the whole rich gets richer story. So their term, this is all invented, by themselves, okay? They were not aware of Simon's model or the work by de Sola Price and so on. Fair enough, big world. So their story is that growth, fair enough, and preferential attachment are the two things driving. And so we'll look at the network version of a rich gets richer thing. So we're going to go through their model. We start with M0 disconnected nodes. It'll be a little bit of math. We'll treat it in the same way they did, and then we'll look at some work later on. This is Krapivsky and Redner. Sid Redner at BU, and they did a really nice thing. So we'll see a much more potent kind of analysis. But let's go through this one to start with. I know it's exciting. Okay. So very simple thing. We're going to have a new node appear. We could make this time step variable in some way, but new nodes are going to start. There's going to be a bunch of them disconnected to start with. And then they're adding M links to the nodes that exist already. Right? So a new node appears. It's going to randomly choose in a particular way. It's going to be preferential attachment. And so it's going to be like our Simon type model. the probability that you connect to node I will be proportional to its degree, right? So if it has the more friends it has already. So again, this is rediscovered. I guess I want to say again that these power law size distributions appear everywhere. I think you're probably aware of that by now. There are many different mechanisms though. That's the thing. This is one of the big mechanisms. It's been rediscovered in different variations. So that's an important one. I'm going to talk about it again. I can't help it. But there are many different mechanisms that give rise to different kinds of power law distributions, sometimes with the same exponent, right? So that's a nasty problem. You can have really fundamentally different mechanisms giving rise to the same exponent, and there can only be one theory, right? So, all right. But these things happen over and again. You're right. We were thrilled with the bell curve when we sorted that out. We're just absolutely delighted by that, and it's amazing. It's absolutely amazing. But the thing that matters for us so much more now, of course, is this, right? Okay. So it's a rich gets richer scheme again, and we've seen it all before with Simon's model. And so this is there'll be a different treatment here, which we'll go through. And I don't think I'm going to force you to do it. Okay. All right. So this is not the term they use. This is Redner and Krupivsky, an attachment kernel. I'll see if I can get through their model. I think that's a reasonable place through the Barabasi-Albert model. That's a reasonable thing to do today. So we have an attachment kernel. So if each node if a node has a degree k, it's going to have this quantity sub k is going to be attributed to it. And so in the original model, it's this, right? This is proportional to the degree. So the attachment kernel is going to be k. So what we'll do later on is think about k to the new. Or you could think about all sorts of other k's. Of course, if you look at a real network growing, you may see what its attachment kernel is. But there are natural kind of ways to play around with it analytically just to explore what happens. And we'll see that it's for k, basically you can get an enormous range of things. K to a power greater than 1, the story really cuts down, and you do get a universal kind of story. And k less than to a power less than 1, again, it collapses. There's less flexibility. But this is a very interesting situation because it makes sense. This is really what a lot of networks this is really how they do grow with this something akin to this linear scaling. It's a very natural kind of thing to produce or to see exhibited in the real world. So its fragility is quite interesting. All right, and important. All right, so then you take this guy and you say, well, the probability that you attach to a node of degree k is derived from these attachment kernels, right? So it's going to be let me do it over here. I'm not doing it properly. Okay, so it's an attachment kernel divided by the sum of all the attachment kernels over all of the nodes. And so in this model, because it's degree k is what your attachment kernel is, then you're summing all of the degrees from I equals 1 to n, where n is the number of nodes at time t. And so that's it. All right. So that's a bit of a we'll deal with this later, but that's a bit of a funny thing because it means you need to know what all the degrees are. Right? If you see a node of degree 7, to figure out what the chances that you attach to it, we've tackled this a little bit before. You need to know what all the degrees are, right? So it sounds very good because it sounds like just a nice random mechanism, but it isn't. There's some sort of load that's required to actually make it manifest. So we'll see how to deal with that later. All right. Yeah, so sometimes randomness isn't really for free. All right, so we know that the number of nodes at time t, well, it's the initial number, m0 plus t, right? And we can change this around. We're summing up all of the degrees, so we could change this into something that gets at our probability distribution we're looking at. Right? We're looking for the frequency distribution of k. So we can say, all right, we're summing all the k's. So a simpler way to do it would be to say, let's find all the nodes, the number of nodes that have degree k, multiply by k, and then sum over all degrees. So that's going to give us the same quantity as this guy here. Right? We want to add up all the degrees. This is a little shortcut way of doing it, which you can see is then connected to the average degree. Right?
How is the attachment kernel AK related to the attach?
Yeah, so in general, it's the P of attaching to K, a node of degree K. Node I will be proportional to A K sub I, right? So that's the idea. And so what you have to do then is say it's in fact equal to A K sub I divided by the sum of all A K sub J's, right? J equals 1 to N. Is that okay? So it's a weight. Each node gets a weight. I mean, it could, then this thing could be 1, right? It could be K squared. It could be log of K. It could be anything you want.
Right.
Yeah.
Okay.
Yeah. Cool. Okay. And so this is the guy we're kind of after. So nk of t. Yeah, I should change it. Is the number of degree k nodes at time t. Okay. So this is a nice way of handling this problem of how do you create the probability of connection at each time t. Well, you don't do that. You actually specify a weighting. Yeah. All right. So you've seen this kind of thing before. So we're adding the n plus 1th node. So the expected change in the degree of the ith node, right? So I has degree k sub I, and this is, we're going to replace, all right, we'll put in n plus 1 here, meaning the n plus 1th node is being added. It's going to be approximately, so here's the probability of attaching to that node times m, because that's how many chances you have, right? This is going to be a small, very small quantity. Right? It's a very tiny chance that you get a shift. Right, so we assume the connection probability is small, and then we're going to throw away this expectation and say that, well, you know, you add the n plus 1th one, the n plus 2 one, and keep going, and it's going to trickle into the distribution all over, right? It's going to build it up slowly. And then we do a sneaky thing. This is different to what Simon did, so here's a departure in this approach. You'll see now that there is not a, when we had this whole probability of an innovation rate, we don't have that, right? That was a different thing, a very, very sensible kind of thing, right? So there's a, probably that the way we framed it was a word was repeated, probably that the next word was a new word altogether, alpha. That's not in here. Okay, so it's not in here. Or implicitly it kind of is at a very certain value, but it's not. Okay, so we're not doing that. We're adding one node each time, and it's going to connect to m nodes. It's going to be big. Those m nodes will be different. So we're going to replace this by, this is sort of a difference of 1 on the bottom if you want. So we're going to put a delta k of a delta t and replace it by d by dt of the degree of node I at time t. And you'll see that this is not quite as elegant as Simon's approach. So we've got this change, and we're going to just set it equal to, which is really the attachment kernel on the bottom, the sum over all of the degrees on the bottom again. Okay. Right, so this is really probability of attach, m. You get m chances to do it. And if we want to be truly careful about it, the time is really the total number of nodes minus m sub 0, because we started with that many, so at time t we actually have, the total number is t plus m0, fine. Okay, so we can clean some things up. The piece on the bottom actually can be re-expressed very simply, right? So it's the sum of all of the degrees at time t, and we started with no links in between the nodes, which is a bit of there's a bit of a sneaky problem there, because you need the reason, the probability that you add is not 1. I wonder what they did with that. Usually the fudge is to kind of just add 1 to the whole thing. have to look at the original paper again. Okay, so if you're adding m links, new node comes in, adds m links, then, and you've done that t times, and there are two n's to each link, so you have 2tm, that's the sum of the degree. Okay. So that's good. So we're going to clean some things up here. This is just repeating what we have. So we had m out the front. These m's are going to cancel, so 2mt on the bottom, and we just get this guy. So that seems pretty doable. So now you have d by dt of k sub I is 1 over 2t k sub I. So simple differential equation. What do you do with that thing? Mathematica. Oh, great Wolfram. What is the answer? Okay. All right. What kind of differential equation is it?
Separable.
Yes. See, you got to say it in another class. All right. All right. The really good ones are the linear, stuff. Right. Okay. Horrible nonlinear things where you approximate it with a linear thing and you get matrices, eigenvalues. Yeah. Remember that? Very nice. Saddle points. All right. You can kind of throw the rest of diff e's away, diff eq's away. Anyway, so it's dk over k, dt over 2t, right? Putting it around, very good. And what do we get? So we get a log on this side, right? Integral of this is a log. Integral of this one is half, well, the half is just sitting here, log t. Right, so what do we get? We get ln of k sub I equals some constant, let's call it k plus log n of t with a half. And we can always make this constant a log of c. Let's do that because that's fun. So we'll just make it a constant, right? So some arbitrary constant, log of c is any number between minus infinity and infinity, so that's good. So this is log n of, and we're going to put this guy up here because that's fun too. So it's log n, and we'll join these guys together, so we get c t to the half. So this guy and this guy are the same thing. Super duper. All right. Okay, so that's kind of a nice thing. We didn't see this really before in the other approach, right? So now we have, this is just one node. Its average degree is growing like t to the half. Yeah. So you can, if you're in front, say you start here, this is time t, you're a node that appears, your average degree is going to start at m, because you start off with m, and then it's going to grow. This is going to be a square root, right? But you know that the ones who come later on are not going to do quite as well. They're still going to have a square root growth, but they're not going to be, they can't catch up, right? It's inherently a Ponzi scheme, the whole thing. I think I actually have this. Okay, good. So we need to find out what this constant is. And we know that the time that the ith node starts, because we've just ordered them, is I minus m naught. Okay, yeah, because there are m naught to start with. And the first few guys started at times 0, the m0 ones. So we just ignore the initial ones. Then we have this kind of business. Okay, so how do we get from this model to here? Okay, so the next thing we have is, good, this will be good. So ki equals c something times this. Okay, so we could make our constant, we could just put our constant in here. If you want, c prime. Kind of, that's all right. We're just going to mess around with things. And we know that when t equals ti start, ki equals, oh, that was the other thing to do. Can't believe it lasted so long. All right. Terrible computer. Really need another Steve Jobs, I've got to say. Okay. It's amazing what it just did. It usually runs out after about 5 minutes. Okay, so yeah. I'm totally lying when I do this. This is a bad plan. So if the idea is to do this. We're going to create our constant by doing this. if we put ti start down here, like we know there's some constants involved here, then we have a nice thing. So when t is ti start, when it starts, this is a 1, and we must have its initial value, which we know is m. So you could do it. You could say, let's put ti start in here, and we know it starts off with m, and then undo everything. You could do it. That's how you could get your. That's how you get your constant, right? So you could be good people and say, right, t to the half. That's what it is. Put ti start here. Ki equals m. They're your initial conditions. You get c, right? That would give you c equals m over ti start to the half. And then you'd stick it all back together. Or you could be a little bit sneaky and kind of see that it must have this form, right? This comprises a constant. So we're just going to use the things we know about it. Ugly, sneaky. Okay, so it's going to do the right kind of thing. And it's only for t greater than ti start, right? So that's important. Then it takes off. So I've said these things. All nodes are, their average degree grows as t to the half, so it's not taking off. Yep. And so the later nodes, of course, they have a larger start, so that's damping. This is the same for all nodes, but the larger this is, the more it's damped down, right? So it becomes a prefactor, and it's just damping it down, right? The larger this is, as this becomes larger and larger, the more it squishes the thing. So it builds in this kind of first mover story, right? The first mover advantage. So we'll teach this in an MBA course. Leave out all the math and say that science shows you this. It's what happens. It's unbelievably true. So in this model, the early nodes are winning, and they can't catch up, the ones that come later. That becomes more and true if it's a much richer gets richer story, right? The growth is k to a power greater than 1, then this is even more extreme, and it's less of a problem as you go down. So it's a Ponzi scheme. Okay. Amway. Yeah. Sorry, maybe some of you have personal fortunes because of Amway. I don't want to. Well done if you have. All right. Okay, so this is a couple of examples. They're starting at 1, 2, 5, and 10. So this is the thing. These are all, right, if you put them on a log scale, you'd see the and started them at the same point, you'd see the slopes would all be the same. But the prefactors are killing them, right? So these guys, they get predictable earnings, but, right? So someone says you all have, it's going to grow like a square root. It's going to be great. It's going to be great. Your prefactor is 10 to the minus 8, minus 20, so that's the bit they'll leave out. We're all the same. We're all, right, okay. All right, so that's interesting. So let's see, I'm gonna tell you the end of this, and then we'll maybe come back and clean up. All right, so we need the degree distribution. That's a characteristic of the whole thing. So all of these guys are taking off. So we do a sneaky thing to figure it out. So we know the probability of, we can make a conversion like this. The probability that if we randomly choose one of the nodes in the game already, the probability that their start time is some value is chosen from a uniform distribution. Right? That's what this is, and it's normalized by 1 over t. So it's of width t, it goes from 0 to t, with a height 1 over t. So we know what that distribution is, so we're randomly choosing one of them. So we've done this sort of thing before, so we already have this result. So we have a connection between ti start and ki, and we have a probability distribution for the start time. So we're going to make a change of variables. So here's ti start in terms of ki. So we can differentiate this guy with respect to k sub I. So this is quite nice. All right, there's a 2 on the bottom, so we get a minus 2 and a cube. Yep. We take the Jacobian, so that's the absolute value. So this guy is going to replace this bit. We'll put the dki up here. The 1 over t is actually going to magically cancel things out, right? So this is our usual connection between the two probability distributions. There's a 1 over t for this piece. dk sub I is sitting there. We're going to replace the Jacobian with the thing we just figured out. These guys cancel, which is pretty magical. And we get an inverse cube power law. Craziness. And it comes from right? It's pretty weird. And here's the weird thing. So this is published in Science. That's what they get, k to the minus 3. They get a power law, and that's the big story. It's a power law. And I'll come back to this later on. But if we go back to these things, right? 4, 2.3, and 2.1. So theory is not plotted on these guys. And we'll come back to that again later on. But and these things you know all about. So that's the upshot. They get a -3. And they get 20,000 citations and giganticness and so on. And, you know, it's good work. I mean, but we kind of knew about it. We just didn't quite keep telling the story to ourselves, right? De Solar Price knew about it in the 70s. Simon knew about a pre-version of it, right? And anyway, so rich gets richer manifested everywhere. So we'll clean up these little details later, next time we talk, and we'll go on to some other pieces. We'll do a better job with it. Totally exciting? All right, okay. Run away, people. Okay.